Hi, I'm Ho Lam. Here I want to present my analog electronics finals, which is the internal of OPAMP LM71 and the low power version. So first, I want to go through the overview and the introduction. So here we're trying to reconstruct the LM71 with uh, 2N222 and 2N2907 transistor, which is PNP and NPN. And then for this simulation, we are assuming all the electrical characteristics like early voltage, beta value, reverse saturation currents. They will be very similar to the 2N222 and 2N2907, since we're using these two parts to rebuild the circuit. So this is our assumption. And then here's the circuit breakdown. I'll go through in detail in each part. So here, this is the schematic, replicated schematic from the datasheet. First, we have a differential amplifier, and then in the center we have a current referencing, and then up here we have current mirror supplying the differential amplifier, and then current mirror supplying to the to different stages. And then we also have a output stages. We'll go into detail later. So for when through the explanation, I'm going to use this setup. I'm going to have a input waveform of 40 microvolt peak-to-peak sine wave at 5,000 hertz. So make sure we're not falling in a cutoff region. And then we are going to supply a 15 volt plus and 15 volt minus. And then right here we're using a feedback value of 5K and a input resistance of 2.5K. We're expecting a gain of 2, since and we're feeding it to the inverting terminal. So the gain should be RF of Rn, which is 2 V over V. And then here's we are comparing the data to simulated LM71. Here's the schematic. So we're using the exact same setup. We're just comparing the performance of the amp. So first, in the center of the circuit, we have a biasing circuit. So the purpose of this is to provide a reference current for different parts to use. So everything is using the same reference. It's followed by this Q12 and Q11 and a resistor in the center, R5 39K. And then all the other stages are built-in current mirror based on this reference current. So right here, we have the input stage. This is a differential input. So we can see the previous reference current is in the center, and then we are getting our current from this current mirror here and current mirror here, formed by Q8 and Q9 and Q10 and Q11. Q10 and Q11 providing current to the Q3 and Q4. This two is differential amplifier, and Q1 and Q2 is acting as a intermediate follower. The purpose is we can increase the input resistance, and then we'll deliver the voltage to the differential amplifier. Okay, deliver signal to the differential amplifier. On Q2 we have an inverting terminal, and then Q1 is the positive terminal of the op amp, and then Q5, Q6, and Q7, and these three resistors down here, they're acting like a load for the input stage. They provide a gain of around 0.6, and the input is taken from this collector of Q6. So here we have our output going out. So we're expecting a gain less than 1. Let's see how the waveform looks like. So after stage 1, this is the output. So we can see it's a bit noisy, and we have a 40 millivolt peak-to-peak input, and right here we have around a little bit more than 20 peak-to-peak input. So this is around 0.6 of gain. Let's see if we put a 2 volt peak-to-peak input. So if we put a higher peak-to-peak input, the noisiness get reduced. We are getting a better image. But this is the first stage, so things will get figured out later. Okay, let's move on to the second stage. So the second stage is a gain stage. The signal is fed to the base of Q18. So let's go back here. So we can see a V out here, and then it's feeding to this Q18 transistor. And then Q18 and Q7 is following a Darlington pair. The purpose is to have the benefit of Darlington pair is we have a beta square, which is going to give us a very high gain. And also Q18 is serving as an emitter follower. So this is going to give us a very high input resistance. The good thing is we can prevent gain loss from the first differential amplifier stage, because if we have a low input resistance, it's going to kill the gain. And then Q17 is a common emitter amplifier, and we're using a active low from this Q12 and Q13 as this current mirror is serving like an active low, and this is known as a Class A amplifier. So I have an example here. Class A amplifier look like this. The loading here, we're using an active low, this current mirror, and then the Darlington pair Q18 and 17 is going to serve like a single transistor. So the outlaw of the current mirror is, however, equation here, and then yeah, pretty much this stage 2 is just a Class A amplifier. It's nothing but the Darlington pair serving as one, and active low founded by the current mirror. So the benefit of having the active low is we have a very high resistance, and we can still deliver the current without disposing too much power. And then on the second stage, you also have a 30 picofarad feedback. This is known as a Miller compensation configuration, and this is going to create dominant pole compensation at around 10 Hz or even lower. We'll see this in frequency response later, and we have a very good frequency response in the lower frequency. And the output of this stage is collected in the Q17 collector, which is here, and this is going to the final output stage. Before we move on, we're looking at the waveform of the second stage. You can see here we have a much cleaner waveform, and then we have a gain around. So we have a gain around. Let's see, zoom in a little bit. So this minus this is around 160. So 320, a gain of 320 around that. Okay, and then let's go to the output stage. So here we're seeing the output stage of the circuit. So the goal of the stage is provide a very low output resistor and still be able to supply a fairly large loading current. So here we are seeing this Q14 and Q12 is forming a Class AB output stage. And this is biased by this R7 and RA and Q16. But mainly is this Class AB output, Class AB configuration. And we're getting this output from here, and the output is fed to this Q20 And notice that Q14 and Q12, ideally they should have a larger area so that they can supply a higher loading current and minimize the temperature effects. So here I have an example of class AP amplifier setup. Q14 and then Q20. When the current is high, when the signal is in the positive side, Q14 is going to be turned on, 20 is going to be off, and then this is going to handle the positive voltage. And then when the signal is negative, this 20 is going to turn on and pull it to negative. And yeah, so basically the upper part handle the positive signal. This P part handle the negative signal, and then in here we have a biasing circuit. We can see Q16 and these two resistor. The purpose of having this is since this is a BJT, we'll have the 0.7 volt drop because of the nature of BJT is going to be turned off. So we have a 1.4 volts voltage is not going to be turned on. So we need this biasing to keep these two transistors be turning on all the time. And then we also have a short circuit protection. We can see here Q15 is protecting this Q14 from short circuit. However, there's a small difference between the textbook example and datasheet. The circuit I'm building is based on the datasheet I have from the LM471. So on the left, this is the picture, a screenshot from the datasheet, and on the right, this is the schematic from the book. You can see on the book we have a Q15 protecting Q14, Q21 protecting Q20. In the actual schematic, we only have one. Since we are trying to compare to the actual one, I decided to go with the datasheet one, but here I'm just going to mention it. And this Q24 is protecting this. So for the one I'm building, we only have this protecting Q14. And then let's move on to the performance comparison. So here we have a side-by-side comparison. On the upper wave, this is my output waveform of the. Actually, this is a 40 millivolt peak-to-peak input with a 0 volt offset. And here on the bottom, we have an actual curve from the real 741. So you can see they're pretty much the same in performance. Now we try another waveform, 1 volt peak-to-peak with a 1 volt offset. Since it's an inverting amplifier, we're expecting a 1 volt offset become a negative 2 offset, and then 1 volt peak to peak become a 2 volt peak to peak. So both of them perform correctly. And then we go to DC analysis. For the DC analysis, all the caps are open circuits, and then we're shorting all the input signal. So here input is gone, and then this cap is open. Here the value of the DC analysis. Not going to go into too details. Here are all the current value, and then here are all the biasing voltage. So yeah, I'm not going to go into detail. I'll continue explaining in the next video, since the software I'm using has a limitation on time. So let's continue in the next part. Okay, let's continue from part 1. So here we have the voltage swing from DC sweep from the actual for 741, and this is my reconstructed one. Here side-to-side comparison. So again, DC V in from -10 to 10, expecting a gain of -2. And comparing it to the datasheet, we're still in the range. So this should set should be around plus or minus 14. So we're still in the range. And then let's go into electrical characteristic. First, let's go through input offset voltage. So here to measure the input offset voltage VOS, we're going to use this schematic, which is same as what we did from lab 1. So here's the equation for calculating that. Not going into too much detail since this has already been done from lab 1. So we're using this equation. We use this setup with a and then we get the value of. So the actual 741 has a value of 9.58 millivolt, which is still a little bit higher than maximum. And then on ours is like way higher than what the schematic said, since is built of BJTs. And then has the input bias current for the positive terminal. We're going to use this equation with R1 of 100 ohm, R2 of 1 mega ohm, feedback of 1K. And then again, here's the equation from lab 1. We're going to reconstruct the circuit, and then we have a so for the actual 741 is in the range between of the datasheet, and then for ours is 8.4 microamp, which is a lot higher than what it say from the schematic, from the datasheet. And then we want to go to the input offset current. So we're going to use this setup, and here are the equations to calculate the I offset. From the datasheet, the max typical is 2 nanoamp, maximum 20, and then we're using RF of 1 mega, and then R2 is equal to R1 parallel of RF, which is 91 kilo. And then here's our value. The actual one has a 7.2 nano, which is still in range. And then our input offset current is close to the actual one, which is good. 7.89 nanoamp. And then common mode rejection. So to do the common mode rejection, we're going to use this setup and then simulate. Since there's a snow day today, school is closed, so I'm not able to simulate this circuit. However, here's the setup. Because there's a limitation maximum of component you can simulate on the student version, and since the lab is closed today, so I don't have the numbers, but here's the setup. With the simulate, we should be able to get the number. And here's the slew rate. Slew rate is described when a waveform is slewed when it's close to the cutoff frequency. So our cutoff is around 33 kilohertz on this setup, on the gain of 2 setup. So here's the formula for calculating the slew rate. And here's the schematic from the book, how we can calculate it, how we can simulate it. So 2 pi times the cutoff frequency, which is 33 kilo, times 2, which is the gain, which is the maximum peak voltage of the signal. So we have 0.4 V per microsecond, which is close to the what the datasheet said. Okay, now we're done with the LM741. We want to move on to the 5-volt version of the CMOS low power op-amp. So here's my design. It's a 3-stage amplifier design. First, we have a input bias at the current bias stage. Here, this is the schematic from the book. I'm reconstructing this on the left side. So this is the input bias. And then on the right hand side, we have a differential amplifier with a current mirror here. So see, this is current mirror getting from this bias circuit. And then here we have another current mirror here as a active low. And then we have a differential amplifier. And then stage 2, we have another just one single CMOS acting as an amplifier. And then this is going to serve as a current supply. And then here we have compensator. Let's go into detail. First, here's the biasing circuit. Here's the circuit from the book. We're constructing this. In PSpice, I'm not able to configure individual width of each transistor, but has the equation to calculate the reference current, and this can be tuned by this resistor over here. And then here in the second stage, we have the differential input. This is the positive terminal, this is the negative terminal, and then this is the biasing for our circuits. And then we have a current mirror. So Q5, what is it? Q5 is a current source. Q12 is a differential amp. Q3 and Q4 is the current mirror. And then for the output stage, Q6 is a common source transistor, and then Q7 is a current source loading, and then we also have a frequency compensation, Miller compensation, 1 pico. So let's look at the output. I'm using the same setup as I used before. No, sorry, actually I'm using a follower here, 5K and 5K. We expect a gain of -1. So we can see here, peak to peak 40 milli, and we have a inverted signal. And then here we try a -2 gain, 5K and 2.5K. And the red one is the input, the green one is the output. So we have a -2 output, which is working. Frequency response, again, this is the red one is the actual LM741. The green one is my low power version. So we have a similar cutoff. It's a little bit lower. And then voltage swing, since our maximum input is 5 volts. And here we have 4 point something positive, and then negative 4 point something on the negative side. Apparently our positive side is very close to 4. Our negative side is close to 5. So that's all for my presentation. Thank you for watching it.